Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing bonding properties of transition metal olefin complexes. This is a very important aspect in transition metal olefin complexes, because bonding determines the reactivity. So, understanding bonding provides a useful insight as to the reactivity of transition metal olefin complexes, and from that perspective we have discussed the interactions that are prevalent for the binding of olefins to the transition metals. And what we had seen is that these transition metal olefin complexes contains olefin interacting with transition metal by two interactions. First one is a olefin to metal sigma donating interaction, and the second one is a metal to ligand pi back donation interaction that happens from the metal onto the ligand empty orbital. Now, these two interactions, that is olefin to metal sigma interaction and metal to olefin pi interaction, are extremely crucial in understanding the reactivity of transition metal olefin complexes. And we had seen that even though both the interactions are important, of these transition metal to olefin pi interaction is kind of very significant. It is significant in two respects. One is that most of the transition metal olefin complexes that have been isolated, they are of late transition metals, which means that the metal has enough electron density on them to partake metal to ligand pi back donation. So, in that way it's one can sort of infer that olefin complexes of transition metal can only be stabilized when the metal has the capacity to participate in metal to olefin pi back donation interaction. And to support this argument, most of the transition metal olefin complexes that have been isolated, they all contain late transition metals. And second point with regard to the significance of this metal to olefin pi interaction is the fact that this presence of this metal to olefin pi interaction increases the multiplicity of this metal olefin bond, and that it becomes more than in a single bond character and partially double bond character. As a result, this transition metal olefin pi interaction also increases the bond energy of the transition metal olefin bond. So, what we see is that the interplay of these two interactions are very important for stabilizing transition metal olefin complexes, and also we had seen that they are important marker for gauging the stability of these complexes. So, with that we are going to talk more about these interactions that occur between transition metal olefin complexes. Now, there is a similarity between an epoxide and transition metal alkene complex. Let us take a look at the structure of an olefin epoxide. Let us say tetracyanoepoxide. And the corresponding nickel cyclopropane system which has nickel bound to L, and that is perpendicular to the ring containing the olefin and the nickel cyclopropane ring. And what it seems over here, this is called nickel cyclopropane. So, this is similar to the epoxide with oxygen on top and nickel replacing the oxygen. Now, these 4 tetracyano groups are not in the plane and are deviated from the plane, and they are deviated by about 32 degrees. So, these 4 tetracyano groups are not in the plane containing C but are below the plane containing C by about 32 degrees. And the same in the nickel cyclopropane is about 38 degrees. So, what one can see is there is a striking similarity between a organic epoxide and a metallocyclopropane intermediate that is formed by eta 2 binding of an alkene. Now, let us sort of discuss this aspect of this metallocyclopropane in bit more detail. Now, one can conceive of metal olefin bond to be of 2 type. One is metallocyclopropane ring where there are 2 covalent bonds, and the other extreme can be olefin attached to the metal where the olefinic double bond is retained and olefinic double bond is completely lost, and in its present 2 metal carbon bonds have been formed. So, this can be sort of spoken about as covalent picture. Let us say this is form A, and this can be called as donor acceptor picture. And this can be designated by form B. Here the donor is the olefin alkane and acceptor is the metal. Now, one can see that in these there are 2 localized bonds, the 2 localized single bonds between the metal and the carbon, and they can be represented as localized orbitals, and they can be represented something like and the other bond can be given as so these 2 can undergo linear combination to give following two types of bonds. One in which all the metal orbital are in same phase, these two covalent bond in same phase, or they can be in different phase. Now, these linear combination thus gives delocalized orbitals. Linear combination of localized orbitals gives delocalized orbitals, which is akin to this donor, both sides of the same phase is akin to the interaction something like this is akin to this, and this part is akin to something like this. So, in this case, this is designated as sigma interaction and this is designated as pi interaction. Now, this left hand side where there is a cyclopropane ring, this is called metallocyclopropane description. And where there is donor acceptor model simple olefin complex, this is called Dvorak Dunkinson model. Now, let us look at these two interaction. For metallocyclointermediate contains two localized 2 electron 2C metal carbon sigma bonds. So, these are classical metal carbon sigma bonds containing 2C 2E types. On the other hand, this contains 1 2E 3C sigma bond and another one 2E 3C pi bonds. So, what we see the difference being that over here there are two localized sigma bonds which are classical 2 electron 2 centered. On the other hand, for the donor acceptor theory, there is one 2 electron 3 centered sigma bond and another 2 electron 3 centered pi bonds. Another interesting difference between the two is, in this case alkene is biradical bidentate and also non-planar. Now, in this case alkene is monodentate and also planar. So, what we see that depending on which description satisfies the metal olefin complex, one can get a bidentate non-planar structure containing two localized 2 electron 2 centered metal carbon bonds, or one can get the delocalized structure which contains one 2 electron 3 centered sigma bond and another 2 electron 3 centered pi bond, and that the olefin in this present case is planar, whereas the olefin in the previous case is non-planar. Another interesting difference between the two structures A and B is in the hybridization of the carbon. For example, this is structure A and this is structure B. In B, the carbon atoms are sp2 hybridized in structure A, carbon atoms are sp3 hybridized. And hence non-planar. And for structure B, since it is sp2 hybridized, it is planar. In B, since this interaction is short, MC bond length is long and CC bond is short. On the other hand, the reverse is true for structure A, which contains this metal cyclopropane ring. In structure A, MC bond is short and CC bond is long, and structure B, the planarity is maintained of the olefin is maintained. In structure A, it is non-planar. Okay. So, now any deviation from this planarity to non-planarity is affected by the metal to ligand pi back donation, which results in formation of the non-planar structure. Now, with that we will move on to a new topic after finishing up this reactivity and bonding aspects of metal olefin complexes. Next, we are going to discuss about something which is related to transition metal olefin complexes, and these are transition metal diolefin complexes. These are closed variety of transition metal olefin complexes, and hence would be treated from the perspective of what we have understood on transition metal olefin complexes when we study these transition metal diolefin complexes. One must realize that there is a distinct difference between isolated diolefin and conjugated diolefin. Now, this is different because now when it comes to conjugation, and as a result of conjugation the bond length and structure of this diolefin would change, and hence is the statement that conjugated diolefin is different from isolated diolefin. The next thing is that metal ligands bonds in complexes with unconjugated diolefin closely resemble the monoolefin complex. In metal ligand bonds with unconjugated diolefin closely resemble monoolefin complexes. Also, wherever there is conjugated and di and oligo olefins having delocalized pi MOs, then they would exhibit different energies and symmetries. Okay. So, structurally what it says that not only energetically, but also structurally there is a change that is brought in with the existence of conjugation on going from monoolefin to diolefin to oligoolefin complexes. Now, with that in mind, let us take a look at how these diolefinic complexes bind to the transition metal. Now, this is a very important phenomenon because one of the reason of this variation or difference between conjugated diolefin with unconjugated diolefin is the fact that owing to the extent of conjugation, the carbon hybridization as well as the distance between carbon bonds are changed. As a result, the conjugated and the unconjugated are structurally different, even though they look like same type of olefinic isomer. Now, with that I would like to conclude about the topics that has been discussed in today's lecture. We have looked at a comparison between epoxides and transition metal cyclopropane intermediates, and what we see is that because of the similar to what had been seen in the epoxide case, where the substituents and the olefin are deviated away from planarity, as a result giving a non-planar distorted structure. Similarly, in metal cyclopropane intermediate, the substituents and the carbon too are deviated and gives non-planar structure similar to what has been discussed earlier. We have also looked at the type of interactions involved in the metal cyclopropane as well as the donor acceptor metal sigma olefinic complex, and what we saw that metal cyclopropane contains two classical 2C2E bonds, whereas the donor acceptor metal olefin complex contain forward sigma donation from the ligands onto the metal and then backward pi back donation from the metal onto the ligand. We have also looked at how these metal cyclopropane and metal olefinic complex change as a result of spectroscopic signature that are associated with them. So, with that I would like to conclude today's talk and would take up the topic in bit more detail, particularly the transition metal diolefin complex in the subsequent lecture. Until then, I thank you for being with me in this lecture and look forward to being with you discussing transition metal diolefinic complexes in the next lecture. Till then, goodbye and thank you.